let's just jump right in. If you work in tech, or frankly, even if you just follow the industry casually, you are constantly swimming in this alphabet soup of terms. Neural networks, LLMs, inference. It's literally everywhere. But today, we're cutting through all that noise. We're going to unpack these buzzwords and build a really solid, structured mental model of how artificial intelligence actually functions under the hood. So the goal for this explainer, simple. I want to make sure you walk away with a crystal clear understanding of the foundational mechanics driving this whole technological revolution. Which brings us to the million-dollar question. What exactly is AI today? Honestly, for decades, that definition has been a moving target. We've gone from these really rigid rules engines to dynamic systems that are now literally writing code and diagnosing diseases. So it's absolutely crucial we ground our definitions before we start looking under the hood. Because while our understanding has evolved massively since the term was first coined way back in 1956. Okay, let's dive into this because to truly understand where we are right now, we have to look at how these foundational ideas are finally being recognized at the absolute highest levels of science. Actually, just look at the 2024 Nobel Prize in Physics. It was awarded to John Hopfield and Geoffrey Hinton for fundamental discoveries in machine learning. You might know Hinton. He's affectionately called the godfather of deep learning. Their pioneering work on mimicking how the human brain stores and recalls information, that paved the way for directly, or at least indirectly, all the advanced AI we see around us today. So this isn't just some fleeting tech trend. It's a fundamental shift in applied physics and mathematics. Here is our roadmap for today. We're going to start with the evolution of AI, then we'll unpack AI, ML, and deep learning. Next up, how machines actually learn, followed by the deep learning revolution. Then we'll look at the fuel, data types, and finally wrap up with making predictions. Okay, section 1, the evolution of AI. While modern models seem like they just dropped out of the sky yesterday, their roots are actually firmly planted in the 1940s and 50s. Back in 1943, we saw the Macaulay-Pitts neuron. This was the very first mathematical abstraction of how a biological neuron might function. And what's crazy is it was mapped out entirely with pencil and paper before modern computers even existed. Then in 1950, Alan Turing gave us his famous Turing test as a benchmark for machine intelligence. By 1957, Frank Rosenblatt invented the perceptron, which was the first true neural network model. And then in 1959, Arthur Samuel officially coined the term machine learning. These foundational years were really all about creating the theoretical language and the math concepts that would define the entire field. Let's move to and see how this builds. Because honestly, it wasn't all smooth sailing. In 1969, this famous book called Perceptrons came out and highlighted the really intense limitations of those early single-layer networks. That actually led to a massive decline in funding, a period we now call the AI winter. But the field survived. In 1986, the backpropagation algorithm was popularized, which finally allowed networks to effectively learn from their mistakes. Fast forward to 2017, and the transformer architecture completely revolutionized natural language processing. And it was that specific breakthrough that directly sparked the era of large language models, or LLMs, that just exploded onto the mainstream stage around 2022. Right, on to section 2, AI, ML, and deep learning. So these terms get tossed around interchangeably all the time, but it helps to think of them kind of like a set of nested Russian dolls. The outermost, biggest doll, that's artificial intelligence. This is the broadest discipline. It's simply the overarching goal of creating machines that can simulate human-like cognitive functions. But here's the kicker. Not all AI actually learns from data. In the early days, we relied really heavily on what's called good old-fashioned AI, or GoFi. This just involved giving a computer rigid, predefined symbolic rules. We explicitly programmed the reasoning into it. It was intelligent, sure, but it couldn't adapt on its own. Now, if we open that up, the next doll inside is machine learning. This is a subset of AI, and it represents a massive paradigm shift. With ML, we totally stopped trying to give machines explicit rules. Instead, we started giving them experience in the form of data. Machine learning algorithms discover patterns on their own. We essentially traded rigid programming for dynamic statistical pattern recognition. It was a real game changer. And finally, the innermost doll is deep learning. This is a highly specialized subset of machine learning. It relies entirely on multi-layered artificial neural networks. And the word deep here, it isn't philosophical at all. It just refers to the multiple layers of artificial neurons stacked on top of one another. These deep networks basically act as universal function approximators. They're capable of automatically learning incredibly complex, abstract representations directly from raw data without us having to go in and manually engineer the features. Let's jump to Section 3, how machines actually learn. Okay, so if we aren't explicitly programming rules, how exactly do they acquire knowledge? Well, think about a list of financial transactions. We've got amounts, times, and merchants. But the most important piece of info is that label at the end. We have human experts telling the system whether a transaction was legitimate or fraudulent. And this brilliantly illustrates the most common paradigm, supervised learning. It's exactly like teaching a child by showing them flashcards with the correct answers attached. We feed the algorithm thousands, or even millions, of these labeled examples, and it just learns to map the inputs to those explicit outputs. But what happens if we don't have all the answers? That's where unsupervised learning comes in. In this paradigm, we drop the labels entirely. We just hand the algorithm raw data and essentially say, hey, go find something interesting. Because it has no explicit guidance, it starts looking for hidden structure, statistical groupings, or even anomalies. So if it suddenly sees a $7,500 jewelry purchase at 3 a.m., it flags it as a massive deviation from the norm. This makes unsupervised learning absolutely perfect for things like anomaly detection or, say, finding hidden market segments in customer behavior. Then we have the third paradigm, reinforcement learning. And this one is wildly different. It closely mirrors how animals learn through trial and error. An AI agent interacts with a dynamic environment and gets feedback as either rewards or penalties. Think about teaching a computer to play chess. We don't sit there and tell it which moves are good. We just let it play millions of games, often just playing against itself at warp speed, and we give it a reward only when it wins. The AI has to figure out what's called the credit assignment problem. Basically, it has to learn which early, seemingly insignificant moves actually led to that long-term victory. Moving on to Section 4, the deep learning revolution.
Let's peek at the exact mechanical engine that makes all of this possible. The true hero here is an algorithm called backpropagation, and it works in 5 pretty elegant steps. First, the forward pass. Data is fed into the network layer by layer until it spits out a prediction. Second, error calculation. We measure exactly how far off that prediction was from the actual target. Third, and this is where the magic happens, the backward pass. The algorithm uses the chain rule of calculus to propagate that error signal backward through the entire network, figuring out which specific artificial neurons caused the mistake. Fourth, the weight update. It goes in and adjusts the parameters, or weights, of those neurons to minimize the error. And fifth, iteration. It just repeats this process over and over and over until the model gets highly accurate.
So the crucial point is, while backpropagation is the training engine, the architectural layout of those neurons matters immensely. And in 2017, the transformer architecture basically changed everything. You see, previous models had to process language sequentially, like word by agonizing word. Transformers introduced this brilliant mechanism called self-attention. This allowed the model to process an entire sequence of data in parallel, dynamically focusing on how every single word relates to every other word, regardless of how far apart they are. This breakthrough directly enabled the massive scale of modern large language models and, well, kicked off the generative AI boom we are living through right now. Section 5, the fuel. Let's talk data types. Any engine is completely useless without fuel, right? And the absolute cornerstone of a functional model is high-quality data. Broadly speaking, we divide this fuel into 2 main categories. First, structured data. This stuff is highly organized. Think tabular data in spreadsheets or time series data like stock prices. It fits really neatly into rows and columns. Unstructured data, on the other hand, completely lacks a predefined format. This is your text, images, video, and audio. It has massive dimensionality. And because of this sheer complexity, different neural network architectures actually had to evolve just to handle them. For example, convolutional neural networks, or CNNs, were specifically designed to interpret the complex pixel arrays of image data, while recurrent networks and transformers handle the more sequential nature of text and audio. And our final section, Section 6, making predictions with AI. All right, once a model has learned and optimized all its weights, we have to actually deploy it to do real work in the real world. This process is called inference. And there are 2 primary deployment strategies here. The first is batch inference. This is for when you have massive volumes of data, but you don't necessarily need the answers right this very second. Imagine an e-commerce site running an overnight job to generate personalized product recommendations for millions of users so they're ready by morning. It's highly efficient. Conversely, real-time inference is for when you need a prediction instantly. If you swipe your credit card, the bank needs a fraud prediction in milliseconds. If you ask a chatbot a question, you expect an immediate answer. Real-time requires some incredibly robust, low-latency infrastructure. Now, what's really interesting about this is that there's actually a clever third option, asynchronous inference. This is kind of a hybrid approach. The requests are put into a queue, and the model processes them as computing resources become available. This is absolutely ideal for things like really large video processing payloads. The user knows it might take a few minutes, so we don't need strict real-time latency, but we still want it handled promptly, without waiting for some massive overnight batch job. It's just a perfect way to balance resource allocation. So we've covered the history, the nested layers, the learning mechanics, the architectures, the data, and finally, deployment. As we transition from single-task models into this wild new era of massive, multimodal foundation models that can process text, images, and video all simultaneously, the capabilities are scaling exponentially. So I'll leave you with this final thought. Armed with a crystal-clear understanding of how these systems learn and process information, what hidden patterns, insights, or totally new innovations could these models uncover in your own data? The tools are out there, literally waiting for you to use them. Thanks for joining me on this explainer, and keep exploring.